Let me now, after having developed these concepts, take 2 or 3 examples where I show how these principles are applied in solving mechanics problems without really going into integration of the equation. As the first example, let us take the case of a bead sliding over a vertical ring of radius r, and I want to know what will be its velocity when it has fallen by a distance x or moved by an angle theta from its initial position. If I were to integrate the equation of motion, I would have to take care of the force that is applied by the ring, the gravitational force on the bead, and so on. If I want to apply the energy conservation principle, since I know that in this case the gravitational field is conservative, so the net energy should remain a constant. So, Ke plus u at the top, that is this position, should remain the same as Ke plus u at say theta. Ke at top is 0. Let me take the u to be 0 here at the ground, so that at the top it is going to be m g times 2r if the mass of the bead is m, and this should be equal to Ke at theta or this distance x plus u at this point is going to be m g 2r minus x, and that gives me Ke at this point 1/2 m v square is equal to m g x, or v equals square root of 2 g x, a well known result. I use this simple problem now to a slightly more complicated problem, where I would ask the question, if there was a particle, it was a very standard problem and probably I have solved it in the past in one of the previous lectures. I want to solve it slightly differently here. If there was a particle which is sliding on top of a sphere, I want to know at which point or at what distance from the top x does it fly off the sphere. So, in this case I know at this point it requires a centripetal force to go over circular path. So, at this point the forces on this are mg in this direction and the normal reaction in this direction. The component of mg towards the center gives it the centripetal force, and therefore, if this angle is theta, so is this, you have mg cosine of theta minus n is equal to m v square over r. As long as n is non-zero and pointing outwards, I know the particle is on the sphere. N equals 0 implies particle loses contact with the sphere. So, at that point I am going to have m g cosine of theta is equal to m v square over r, and therefore, r cosine of theta is equal to v square over g. I have already calculated v square. So, we have r cosine of theta equals v square over g, and if I look at this problem again, I have this r, this is theta, so that this is r cosine theta, and you see that r cosine of theta is equal to r minus x, and we have already calculated that v square is equal to 2 gx, and therefore I have r minus x equals 2x, or x equals r over 3. So when it travels down a distance of r by 3, it is going to fly off the sphere. Another problem where I am going to now combine the principle of momentum conservation and principle of energy conservation is going to be solved now. Let us take a particle of mass, say 0.1 kilogram, traveling in this direction with a speed of 1 meter per second. It hits another particle of say 0.5 kilogram, and after the collision the two particles travel, one with speed v1, this is 0.1 kg, and the other particle with a speed v2, this is 0.5 kg. We wish to find v1 and v2. Although you may have seen this problem in the past, it does not hurt to solve a simple problem to start with. So first I apply linear momentum conservation. Because there is no external force, these things are moving in a horizontal plane, therefore I must have 0.1 times 1, that is the initial momentum, must be equal to 0.1 v1 plus 0.5 v2. This is the momentum to start with. This particle has no velocity, so 0 momentum, and therefore I have 1 equals v1 plus 5 v2. That is my equation 1. Since there is no external force, so potential energy remains the same. The kinetic energy should remain the same if we assume the collision to be elastic, and therefore Ke initial is equal to Ke final. I have not taken potential energy u into account because it remains the same, or on a horizontal surface it does not change, and therefore I must have 1/2 times 0.1 times 1 square, that is initial kinetic energy, final kinetic energy, both particles are moving, and therefore 1/2 times 0.1 v1 square plus 1/2 times 0.5 v2 square, and this gives me half cancels. This gives me 1 equals v1 square plus 5 v2 square. This is my equation number 2. Equation number 1, let me rewrite it once more. 5 v2 is equal to 1. Solve these two equations to get v1 and v2. Let us substitute. So I take the value of v2, which is 1 minus v1 over 5 from the first equation, and substitute in the second equation to get 1 equals v1 square plus 5 over 25, 1 plus v1 square minus 2 v1, this is 5, and therefore I get 5 is equal to 5 v1 square plus 1 plus v1 square minus 2 v1, or 6 v1 square minus 2 v1 minus 4 is equal to 0, or 3 v1 square minus v1 minus 2 is equal to 0. This gives v1 equals 1 plus minus square root 1 plus 4 times this, 24 over 6, and that gives you either 1 meters per second or minus, this is 5 2/3 meters per second. This is a trivial solution, as if the collision did not take place, and this is the solution of interest, in which the particle 1 hits particle 2 and goes back with this much velocity. So I get v1 is equal to minus 2/3 meters per second, and if you recall, I had 1 equals v1 plus 5 v2, and this gives me 5 v2 is equal to 5/3 or V2 equals 1/3 of meters per second. I gave these two simple examples in one-dimensional case to show you how the conservation principles make solution easier. Notice that I did not have to integrate over a force over time. All I did was use the fact that momentum is conserved and energy is conserved.